Hello class, we're about to start section 4.6 and it actually starts on page 389. It says your results may vary. Our learning objectives is to compute measures of variation for a given data set, to interpret standard deviation for a data set, make meaningful comparisons of standard deviations for two data sets, and analyze the procedure for computing standard deviation. Okay. Now at the bottom here, it says the simplest measure of variation that we'll study is the range. The range of a data set is the difference between the largest and smallest values in the set. So we go over here to page 390. It says the first list below is the weights of the dogs in the first picture, and the second is the weights of the dog in the second picture. Find the mean and range for each list. Now remember, the last time we did the mean, we actually used a table, and I want to incorporate that table now as well. So we'll hit this plus sign, hit a table. Now in the X1, we could put in the first picture results, which is the 70, 73, 58, and 60. Now we can make Y1 the second picture, which is the 30, the 85, the 40, the 125, the 42, 75, 60, and 55. Now it doesn't matter that they're not the same length because we're not graphing here. We're just doing our mean value here. And then the range, we could actually do that as well. And I'll show you how to do the range with your table. So the first thing we would do here is hit the keyboard. We will go to functions, and then we will go to stats. Now we want the mean. So we'll put the mean, and we know X1 is the first picture. So we'll do the mean of X1, which will give us 65.25. So the first picture, so I'll put first picture mean is equal to 65.25. So I'm going to do the second picture mean. So we can make this Y1. Backspace this. Well, actually I should have did it this way, but this would be Y1 and the mean will be 64. So now we have the mean of the first picture, the mean of the second picture, and we should put pounds here. All right. So now the next thing we want is the range. Now, of course, because we have a low amount of numbers here, it's easy to kind of tell the range here. So let's just do this. We'll go first picture range, and then second picture range. Now, with the first picture, we have the highest value minus the lowest value. So that'd be 73 minus 58, which actually give us, let's see, 15. So it'd be 15 pounds. So that would be the range here. So the second picture, the highest value is 125, the lowest is 30. 125 minus 30 is 95 pounds. Now, this was kind of easy to do because we had not that many numbers that we had to choose from. But let's imagine if we had to do this with like 20 or 30 numbers and they were all close to the same value. There's a way you could do this in a calculator to find the highest and lowest value. So after you type everything in your table, you can go to function, under stat, and you can click minimum, and then X1. So the minimum value here was 58. And then we also have in the function, we have a maximum value. The maximum value, x1, it gave us 73, max minus the minimum. And then we would get 15. Or you could do this. You could even get fancy with this. You could do the max value. Well, since it's already here, since we had a max, we could do minus, and then we could go here to the minimum. Max minus minimum, it gave us 15. So this is one way you could do it when you put it in the table. All right, so now we go here to problem number 2. It says, describe what you notice about the range and mean for each group of dogs. So the first thing I notice is the mean values are almost the same. The range is significantly different. So their variation is different. Now we go here to number 3, because before we go here, if we look at the range, this range here is only 15 pound different. This range here is 95 pound different, which is a very big difference in their values. Now we go here to number 3. Why is the range somewhat limited as a measure of variation for a data set? And it only uses the smallest and largest values. And ignores all others. That's why it's so limited as a choice. Now, we move over here to the back. It says standard deviation. The range is a limited measure of variation because it ignores all the data except the highest and lowest values. If most of the values are similar, but there's just one unusually high value, the range will make it look like there's a lot more variation than there actually is. For this reason, we will next study standard deviation, which is much more reliable and commonly used measure of variation. Standard deviation is a little tricky to compute. Eventually, we'll learn how to use technology to handle the computation, which will allow us to focus on interpretation. But first, we'll develop a procedure for computing standard deviation by hand. This turns out to be useful even if you never actually do compute it by hand, as it really helps you to understand what exactly standard deviation measures. This is a bit of an oversimplification, but it's still very useful in understanding what standard deviation is designed to measure. Standard deviation essentially describes the average distance that each data value is away from the mean. Read the description of standard deviation in italics above carefully again. A standard deviation essentially describes the average distance that each data value is away from the mean. Why does standard deviation provide a very reasonable way of describing how spread out a data set is? This is because it considers every value and how far they spread out from the mean. Which is kind of a center value. Interpretation of standard deviation. Standard deviation that's large relative to the mean tells us that the data values vary pretty widely from the mean. A relatively small standard deviation means that most data values are clustered fairly close to the mean. Now it says standard deviation comes in two delightful flavors, population and sample. As we saw in lesson 4.4, in many cases data are based not on every single member of a population, but rather a representative sample. When the standard deviation is computed for a data set derived from an entire population under study, it's called the population standard deviation. When it's based on data derived from a representative sample of a larger population, it's called the sample standard deviation. As we begin our efforts to develop a formula that accomplishes what we want standard deviation to do, try to focus not so much on just doing the arithmetic, but the interpretation of what each step is accomplishing. The plan is to find the standard deviation for the weights of the 8 dogs pictured in the lesson opener. Find the mean weight. We already did that, so we can actually do that. This mean weight is actually over the second picture. So if we go back on the other side, the second picture mean was 64 pounds. So we could put 64 pounds. Standard deviation is a measure of how far the data values vary from the mean. So it makes sense to begin by computing the mean. Now listen, what we're going to do now, we're actually not going to go over this next page because we are going to cover a lot of this in the next lesson. So we're actually going to flip over to page 394. And we're going to look at the formula down here at the bottom. It says formulas for sample and population standard deviation. Now it tells us what each of these values are defined as. The capital X represents each data value. So the sample and the population both has a capital X, and it means the same thing. The X bar is the mean of the sample. So you do not see an X bar in the population, it's just for the sample. Now this mu symbol here is the mean of the population. So this mu symbol here would be the mean of the population. So these two basically mean the same, it's just that one is for the sample and the other is for the population. Lowercase n is the number of data values in the sample, and uppercase N is the number of data values in the population. So there are some slight differences, but we get the gist of it. So now, we flip over here to the back. Now, on the back here, it's basically telling you how to type this into your TI-84 calculator, but we're actually using Desmos here. Now, if you want me to show you how to do this in the TI calculator, you could contact me and I could show it to you very quickly. As a matter of fact, let me see if I could pull this up real quick. I might as well pull it up. Okay, so let's say that you were using this TI calculator instead of Desmos. So what you would do, let me pull back let me go back here. I want to go back to picture, let me go to picture 2. Okay, say we was trying to find all this information in regards to picture 2. So first we will go here to stat, we would press enter, and then we would type in L1. So picture 2 had 30, what was that, 85, 40, 125, 42, 75, 60, and then 55. Okay, so now we put these values in the calculator. Now we want to get to where it says 1var stat. So what we could do is press stat, go to calculate, and press enter on 1var stat. And you have to make sure that L1 is here. Press enter, make sure nothing is behind the frequency list, and then you would calculate it. Now, what this does is this here. Remember, for picture 2, we did calculate the mean. It gives us the mean. Even though this is all done as a sample, but if we were doing population, as you see here, it shows population. So the mean is going to be the same whether it's for the sample or population. So your mean is 64. This right here is the sum of x. This is the sum of all the values. You don't have to really worry about that. But here, this is the standard deviation for the sample. This is the standard deviation for the population. But let's keep going down here. It gives us the minimum value. It gives us how many values we had. It gives us the median as well, which is interesting. And it gives us other information as well. But the main thing that you would be looking at, most likely, is the mean, whichever standard deviation we're using, whether it's sample or population. And then you also may look at the median as well. But this is how you would get this in the TI-83 calculator, or TI-84 calculator, I should say. All right. So now we move on to page 396. Now it says here, word on notation. We use a lowercase s to represent the sample standard deviation for a data set. The symbol SX is simply what's used on the calculator screen. Similar, we use a lower Greek symbol to represent population standard deviation, not symbol X. All right, so now, not the lowercase sigma x. Okay, now the table below shows the number of arrests in the United States for possession of marijuana in thousands for the years from 2005 to 2014. All data was gathered from the annual Uniform Crime Report published by the Federal Bureau of Investigation. Find the mean and sample standard deviation for the number of arrests. Includes units. Okay, so what we could do, I'm going to go back here. Well, let me use this other table that I had. All right, so let me get rid of these values. All right. So now we have this table here. Only thing we need is the arrest data. We don't need the years because we're not graphing here. So we have 569, 547, 640, 620, 620 again, 614, 541, 543, 503, and 516. Okay, so we put in all the data. It says find the mean and sample standard deviation. So we know how to find the mean. We'll click here, go to functions, hit mean, hit X1. We have 573. So since it's sample, we'll put the X bar, and it'll be 571.3, which is basically, because remember this is in thousands, this would be 571,300 arrests. That would be our mean. Now we want the sample standard deviation. So we'll go here, go to functions, and then what you see here is the standard deviation. We will hit here and then hit X1. And then since this is 1 decimal place, we can round that to 1 decimal place. So we will have, well, we could use S since we're writing this out. It'll be 48.7, which is 48,700 arrests. Okay, number 2. Why was it appropriate to find sample standard deviation rather than population? Okay. We are trying to generalize a set of years. Then we must use a sample instead of population. So remember, we're just taking a sample because we're just doing a set of years here. All right, now it says standard deviation is easiest to interpret when compared to the size of the mean. For example, a standard deviation of 10 in a data set with mean 20 indicates a much wider spread than a standard deviation of 10 in a data set with mean 200. To help make this easier, we can find the relative standard deviation, also known as the coefficient of variation. This number, usually denoted C of V, is the standard deviation divided by the mean. It's literally what percent of the mean the standard deviation is. In symbol, we have C of V is equal to S over X bar. C of V is equal to lowercase sigma divided by the mu for population data. So for 3, find the coefficient of variation for the preceding arrest data. What percentage of the mean is the standard deviation? So we have C of V is equal to S, because we know this is sample, over the sample mean. So it'll be 48.7 all over the sample mean, which is 571.3. Now we can put this in our calculator. 48.7 divided by 571.3. So this would, if we went to 3 decimal places, it'd be approximately 0.085, which would give us 8.5%. So the standard deviation is 8.5% of the mean. Okay, now we move on to the next page. Now it says, do you think the standard deviation and coefficient of variation for this data set will be more likely to be used in an argument by someone that is in favor of legalizing marijuana or against? It could go either way, because 8.5% is very low. So a person in favor could say, in favor of it, could say, why waste resources for such a low number? A person against can say the number is low because of police diligence. So number 5, it says find the coefficient of variation for the 8 dogs from questions 5 through 11 in the class portion. Compute it to your answer to question 3 on the previous page. What can you conclude? Now, basically, if we look here, as far as the mean is concerned, this is actually the second picture. So that was 64 pounds we had discovered back on the previous pages. Now we just did the standard deviation as well on problem number, what was that? I think that was problem number, oh, we actually didn't do the standard deviation. Okay, so we need to go back and do the standard deviation of this data. So what I want to do, I'm going to create a, well, matter of fact, I could just put it here under the Y1 instead of going to a whole nother table. So going back here to page, if we go back here to page 390, in the second picture, we had 30, 85, 40, 125, 42, 75, 60, and 55. All right. So now we will find the standard deviation, and we can make this Y2. So, I mean Y1. So with that, our standard deviation would be, our sample standard deviation would be 30.7 pounds. All right, so now we'll do the coefficient of variation next. So we have CV is equal to the standard deviation, which is 30.7 all over 64, which is equal to 0.48, which is about 48, which is 48%. So it says, so we have this answer here, which is 48%, and it says compare it to the answer from question 3. Now remember, question 3, the coefficient of variation, I'll write that here, was 8.5%. So basically we could say the dog data varies much more than marijuana arrests. Okay, now we go down here to problem number 6. It says for questions 6 through 8, identify the data set that is likely to have a larger standard deviation. Make sure you explain your reasoning, like with sentences and stuff. Okay, we got data set 1, and then we have data set 2. Now, if you look at data set 1, now they want us to identify, if you notice, these numbers are real close together. Even the highest number is 16 and the lowest number 10. They're not that far apart. But if you look here, the highest number here is 31 and the lowest is 2. So data set 1 actually is data set 2 has a larger range. So it would be expected to have higher variation. Okay, number 7. Data set 1, 40-yard dash, times for starting running backs in the NFL. Data set 2, 40-yard dash times for every student in your math class. Okay, data set 1 would have less variation because each of the athletes would have similar times. In data set 2, fitness levels most likely would vary a lot. Okay, now, and the reason why we could say that about the the NFL running backs is because I could not see some of these teams paying a lot of money to get a running back that is way lower than everybody else. So they would get someone that has similar speed, maybe not as fast, but close enough. Okay, number 8. Data set 1, average monthly high temperature in Chicago. Data set 2, average monthly high temperature in Los Angeles. Okay, now, data set 1 would vary more because of extreme temperatures. Okay, number 9. It says a professor has 2 sections of Math 115 this semester. The 8:30 a.m. class has a mean score of 74% with a standard deviation of 3.6%. The 2 p.m. class also has a mean score of 74%, but a standard deviation of 19.2%. What can we conclude about the students' averages in these 2 sections? The 8:30 a.m. class scores should be similar and vary slightly. The 2 p.m. class scores should vary significantly and will be very different. Okay, we're not going to do number 10, so we will stop here at number 9. Now, before we go on, I do want to talk to you all about what's upcoming. We have Project 4, which is going to be due this Saturday. We have the final exam review, which I will show you here where you can access the final exam review. Let me move this over here. All right. Now, what you would do to access the final exam review, you would, well, first let me let this page load. All right. You will go here to JetNet. And you will scroll down till you get to exam review. And click on it, of course. And all 4 of these are the final exam review, including your midterm. So remember, we did the midterm part 1 and 2. If you need to refresh yourself, please look back over the midterm, part 1 and 2, and then the final exam, parts 1 and 2. That would be the review. There is no check assignments for section 4.6 and 4.7. So there are no check assignments. The only thing that you're concentrating on for this week, you will concentrate on finishing up your project 4, your homework. You do have check assignment 4 or 5, which is from the notes that we had last week. So you would need to complete that today, check assignment 4 or 5, but there is no check assignment for section 4.6 or 4.7. So you have to remember that there's no check assignment for 4.6 or 4.7. Now your homework, I believe your homework is due this coming Sunday. So please make sure you get that done. And then if you have not turned in project 3, unless I told you otherwise, your project 3 is due today. There is one student that I had to extend it until tomorrow. So that would be, your project 3 would be due. Now I will be sending this video out pretty soon over 4.6, but I am going to cover 4.7 as well. And then we can start on this final exam review. Now I have not received any emails from any of you concerning the final as to whether or not you need to change your final date for the final hand. All right, so with that being said, we are going to get into section 4.7, and let me do that now. Okay, section 4.7 actually begins on page 405. Oh, one other thing about the final. The final is going to be set up very similar to what we did for the midterm, meaning you will have to go to the Zoom link, and then after you do the Zoom link, you will come into the class and I will give you the password to the final. And it's over 2 days. It's next Tuesday and Wednesday during regular class time from noon to 1 p.m. So, just to let you know. All right, now, oh, and there are no extensions on the final. So, lesson 4.7, it says just a normal day. Learning objective is to recognize characteristics of data that are normally distributed, understand the connection between area under a normal curve, percentage and probability, make an educated guess about the empirical rule, then use the rule to calculate percentages and probabilities. Number 4, compare data values from data sets using z-scores. Okay, now we go here for 4.7, number 1. It says list some things that you think might be normally distributed. Try not to focus strictly on physical sizes. Okay. Excuse me. We will have IQ scores, finish times in a race, and scores on an exam. Those are a few that you would expect to be similar or normally distributed. Okay, now we move on to page 406. Now it says here, suppose a researcher selects a random sample of 100 adult women, measures their heights, and constructs a histogram. The researcher would probably get a graph similar to the one shown below. All right. It says, notice that we omitted a scale on a horizontal axis. Put in a scale that you think seems reasonable based on the description of the histogram. What do you think the value right in the middle of the horizontal axis represents? Okay, so first of all here, we will put, this will be women's heights. And then we will put that in feet, and inches. Now we could have just done it in straight inches or straight feet, but we're doing feet and inches. So we could say on the low end, we could have 4 feet, 7 inches. And we can go up by 3 inches. So 4 feet, 10 inches. Then we could have 5 feet, 1 inch. 5 feet, 4 inches. 5 feet, 7 inches. 5 feet, 10 inches. And then 6 feet, 1 inch. Those are some values we can have here. Now it says, notice that we omitted a scale. We did all of that. What do you think the value right in the middle of the horizontal axis represent? That would be the middle value is the mean. That's what the middle value would be. Next, the researcher decides to go big or go home, and she chooses big. She dramatically increases the number of women in the sample, and since she has more data to go on, makes the class narrower as well. Happy with the results, she adds even more women to her sample and makes the classes even narrower. The results would most likely look like the next two graphs, which we see here. Now, let's use some imagination. Suppose that our researcher has magical powers and can continue adding data and improving her histogram until there are infinitely many data points. Wow, that's a lot. Instead of drawing boxes, draw a smooth curve that you think the histogram will become in the long run. All right, so I'm going to try my best here. But this is what I think this would kind of sort of look like. Of course, it should be a little smoother here, but so it looks something like this. All right, almost like a bell shape. Okay, now we go to the back. If all went well, you've just drawn your first normal probability distribution. We'll see plenty of examples in the remainder of the lesson if you're unsure how well you did. How does the drawing relate to the maple seed pod example from the opening paragraph of this lesson? Now, if we go back to the maple seed pod, this is on page 405. If you notice here, if we did draw a graph here, it would go very similar to what we had. So it'll be very, very similar. So we will put very similar. The largest number in the middle. And less on either side of the middle value. So it basically would be the mean. A probability distribution that plots all of its values in a symmetrical fashion, and most of the results are situated around the probability's mean, is called normal distribution. Values are equally likely to plot either above or below the mean. Grouping takes place at values that are close to the mean and then tails off symmetrically away from the mean. Now, if we look here, it says, what is the mean height of American women? Now, if you look here, this is actually in the middle here. The mean height would be 63.7 inches. That would be the mean height, which is almost 5 feet 4 inches. Very close, but not quite. All right. So now we move on to the next page. It says, what percentage of American women are between 57.4 and 59.1 inches tall? So we have 57.4 and 59.1 inches. And if you notice here, we have this decimal of 0.034. So now we're going to change that to a percent. It'll be 3.4%. If there are 31,806 women in the stands for a college football game, how many of them would you expect to be between 63.7 and 66 inches tall? All right, so we'll go back here. 63.7 and 66 inches. So we have 0.303. So we'll take that value. So it says how many would we expect? So we would take this value and multiply by the 31,806 women. So we'll multiply this. Let me see, 31,806. So this would give us approximately 9,637 women if we round. Now, we come down to the bottom here. It says, according to recent research, the mean height for women in the U.S. is 63.7 inches, which you already knew, right? And the standard deviation is 2.7 inches. The normal graph below is marked with the mean and heights that are 1 and 2 standard deviations above and below the mean. Now listen. Let's talk about standard deviations above and below the mean. What this is saying is this here. We know 63.7, according to this exercise here, is the mean. And they tell us the standard deviation is 2.7 inches. So when they ask us one standard deviation above the mean would be for you to add the standard deviation, add one time the standard deviation to the mean. So if I asked you what was the number one standard deviation above the mean, you would take the mean, add the standard deviation, and that number would be one standard deviation above. Now if you wanted to do two standard deviations above, you would just add the standard deviation twice. And then 3, you would add it 3 times. Okay, now, so this is 96.1 is 3 standard deviations above what the mean is. Oh, you know what? I'm sorry. I made a mistake. I didn't put the decimal here. Okay, 71.8 is 3 standard deviations above. Now, when you say below the mean with your standard deviations, you will subtract 1 standard deviation below the mean. You will subtract the standard deviation 1 time. 2, you will subtract it twice. And then 3, you will subtract it 3 times. And that, whatever that number is, that will give you your answer. Now, with that being said, as a matter of fact, let's go back up here. I want to show you something really fast. Let's just say we only went 2 standard deviations above the mean. If you look here at this graph here, you have the mean. 2 standard deviations above is 69.1, and 1 standard deviation above is that 66.4. So you see, this is how they got the numbers. Now below, one standard deviation below gave us this 61. 2 standard deviations below gave us the 58.3. So that is how they got the numbers. Now, we move on to the next page. Now it says number 8. The total shaded area on the entire graph is 1. And this is true for any normal distribution. Explain why. Think carefully about what we know regarding area under a normal curve. The area represents the percentage in the range. All possible values under the curve must equal 100% or 1. Now, number 9, make an educated guess as to what percentage of the total shaded area is between 61.0 and 66.4. What does it tell us about women's height? Okay, we have to go back here, and it says from 61 to 66.4. That looks a little bit to be over half. So I would say maybe around 60%. And this percentage of women in the population between 61.0 and 66.4 inches tall. Hey, number 10, based on your answer to question 9, estimate the percentage of area between 63.7 and 66.4. 63.7, 66.4. That's like halfway, so I would say about 30%. Okay, now make an educated guess on a percentage of total shaded area between 58.3 and 69.1. 58.3 and 69.1. It looks like all of it except for maybe about 10%. So I would say about 90%. Now it's time to see how you did. Okay, so we have to go on to the next page. And we look here. Now these have the percentages. Remember these two values here, we said, well, I put down that it was about 60%, but this is like 68.2, and then and so on. So, and then half is 34.1. So now we're going to take this, and if you notice here, we have the X bar, which is the mean. We had a mean plus 1 standard deviation plus 2 standard deviations plus 3 standard deviations. And we know repeated addition or repeated subtraction is basically multiplication. So when I was here on the calculator, when I subtracted 2.7 twice, I could have did 63.7 minus 2 times 2.7. Because we know repeated multiplication is, repeated subtraction is the same thing as multiplication. And I'll just show it to you. Better to show it than just to talk about it. So we have 2 parentheses 2.7. And it should give us the exact same answer above. And it'd be the same thing for addition as well. All right. So we come down here to this problem. And if you look here, it says, man, I love M&Ms. Can't get enough of them. When I buy a bag, the last thing I want is to get shorted. So, how many M&Ms is enough? According to a fascinating post on joshmadison.com, the mean number of M&Ms in a standard vending machine bag is 54.6, with a standard deviation of 1.3. Assuming that the number of M&Ms per package is normally distributed, which by the way it more than likely is, fill in the blanks in the diagram below, which represents the distribution of M&Ms in a standard package. Think number of M&Ms. Okay, so they told us here that the standard vending machine bag is 54.6. That is the mean. So this will go here 54.6. And the standard deviation is 1.3. So all we have to do to find out going up is keep adding 1.3 to the 54.6. So this would be 55.9. Add another 1.3. This would be 57.2. And another 1.3 is 58.5. And then going below, we would subtract. This would be 53.3. Subtract 1.3 again. This would be 52.0. And subtract 1.3 again. This would be 50.7. Now, it says, if you buy 1,000 packages of M&Ms, how many bags would you expect to have between 53 and 56 M&Ms? So if you look here, this is 53 to 56 about. So if you look at the percentages here, you have 34.1% plus 34.1%, which is 68.2%. So you would take the 1,000 and multiply it. We'll change this percent to a decimal. Be 0.682, which would be 682 bags. Now, it's likely over 99% of all bags have between blank and blank. It'll be 50 and 59. What percentage of bags would you expect to have at least 55 M&Ms in them? Okay, so if you look here, 55 M&Ms, we basically go, let's see, at least 55. So that's 55 or more. So we would go here and higher. So that'll be 13.6%, 2.2%, and then a 0.1%. So you would expect 15.9% to have at least 55 in them. So you can't go lower than a 55. Now we go here to the back. It says, what percentage of bags have less than 52 M&Ms? How bad would that stink if you got it? Okay, less than 52. So we would go here, and less than 52 would be that 2.2% and a 0.1%. So that'll be 2.3%. Okay, 17. How unusual would it be to get a bag with more than 58 M&Ms or less than 52? So if we go more than 58, that'll be 0.1%, or less than 52, we will have these two values here. So it'll be 0.1% plus, it'll be 2.2% plus 0.1%. So it'll be about 2.4%. Now, we move on here. We really don't have that much more to go, but I will stop. Well, let me do this last problem and then I will stop here. It says a quantity that can vary randomly from one individual trial to another, like the number of M&Ms in a randomly selected bag, is called a random variable. Why? Because it's random, it can vary. See, math does make sense. If you're really sharp, you may have thought about the connection between the percentages we've been calculating in this lesson and probability. If you haven't, we're going to ask you to do so now. Using what we know about area under a normal curve, and percentage of data values. What does the area under the curve between two data values tell us about probability for a random variable? The area is the decimal form of the percentage. The decimal form is the probability. Okay, so there's no really sophisticated tricks here. So that's basically it. Now, we're going to pick up where we left off the next class period, and please remember to do all of those activities I asked you to do. And I will talk to you all in class tomorrow.